The Caribbean's postcard scenery of turquoise seas and swaying palms hides an older, deeper mystery. Who first set foot on these islands and how did they get here? Cutting-edge, ancient DNA research is finally illuminating the long-shadowed migration routes that brought humanity to this tropical frontier. By extracting fragile genetic fragments from cave burials, shell middens, and sun-bleached bone, scientists are piecing together a story of seafaring hunter-gatherers, ceramic-making farmers, and surprising links across thousands of kilometers of ocean. Want more deep dives into archaeology, genetics, and hidden histories? Hit subscribe. Long before pottery wheels spun or manioc gardens took root, small bands of expert mariners were already threading the island chain. These archaic peoples lived as hunter-gatherer fishers, paddling dugout canoes between rocky coves, harvesting conch, sea grape, and guava, and napping shell or stone into adzes and spear points. Camps were ephemeral, often little more than shell middens and hearths, but their maritime savvy was formidable, letting them leapfrog hundreds of kilometers of open water at a time. Around 2,800 years ago, a second wave arrived, carrying fired clay vessels, polished stone celts, and domesticated crops. These ceramic-age settlers established permanent villages, cleared fields for maize and cassava, and left behind rich stratigraphic layers of painted pottery that archaeologists still use as time markers today. Linguistic and genetic clues tie them to Arawakan-speaking farmers of northern South America, and their expansion followed a stepping-stone route through the Lesser Antilles before spilling into Puerto Rico, Hispaniola, and Cuba. The stage was set for two parallel societies whose interactions, or lack thereof, remain one of the region's enduring puzzles. Recovering ancient DNA in the Caribbean is an uphill battle. Heat, humidity, and acidic soils shred the double helix into chemical confetti within decades. For years, archaeologists could only infer migration stories from pottery styles and toolkits, valuable clues, yet silent on blood ties. Enter hybridization capture, a molecular angling technique that deploys billions of microscopic hooks. Each hook targets a specific single nucleotide polymorphism, SNP, reeling in fragments that match 1.2 million predefined coordinates across the human genome. Even when DNA is 99% dust, this method can salvage the remaining 1%. Using this approach, a Max Planck Copenhagen team analyzed skeletal remains from 16 sites: caves in Cuba, shell middens in Puerto Rico, burial mounds in the Bahamas, and rock shelters in Guadeloupe and St. Lucia. Against the odds, they retrieved readable genomes from 93 individuals spanning 3,200 to 400 years before present, building the first region-wide genetic dataset for Caribbean prehistory. 52 of the 93 sequenced individuals come from shell-midden caves in western Cuba, the oldest dating to approximately 3,200 years before present cluster tightly, pointing to a long-lived island population rather than a revolving door of newcomers. One skeleton, CIP-00009 from Cueva del Perico, breaks the mold. Its DNA shares more alleles with 5K-year-old burials on California's Channel Islands than with later Caribbean groups, hinting at a bold Gulf Stream voyage from North America or gene flow along the Florida-Yucatan corridor. Principal components plots park the Cuban archaic cluster far from modern Amazonian, Mesoamerican, or Andean populations, on a branch that split before most living Native Americans diversified. Formal F4 statistics confirm this early divergence and quantify the Californian affinity. Other Cubans, e.g. GY002, carry faint South American signals, favoring at least two archaic migrations, one northern, one southern. Far from a backwater, Cuba was a crossroads for experimental sea routes in the mid-Holocene Atlantic. 41 individuals dated between 1500 and 400 BP, spanning Cuba, the Bahamas, Puerto Rico, Guadeloupe, and St. Lucia, form a tight genetic cluster that overlaps almost perfectly with today's Arawakan-speaking Piapoco of Colombia and Venezuela. Their genomes display none of the early branching signals seen in the Cuban archaic sample, confirming that a wholly new population had entered the archipelago by approximately 2,800 years before present. QPAD-M ancestry models fit a stepping stone spread. Small groups leapfrogged from the Orinoco Delta into the Lesser Antilles, then fanned west to the Greater Antilles. Each island shows a gradient of genetic drift that increases with distance from South America, just what you'd expect if voyagers paused, grew, and launched new expeditions one island at a time. Despite centuries of overlap, ceramic genomes contain virtually no archaic ancestry. Only one Puerto Rican individual shows a modest 13% trace. Whether mountains, reefs, or cultural borders kept the communities apart, gene flow was the exception, not the rule. Mitochondrial haplogroups B2, C1b, and C1c dominate the ceramic burials, while Y chromosomes cluster in QM3 lineages, both common across Amazonia. The coincidence of maternal and paternal markers reinforces a cohesive migration rather than ad hoc intermarriage with earlier islanders. In most prehistoric settings, neighboring groups intermarry within a few generations. Genetic signatures blend like wet paint. Yet, across the Caribbean, two populations coexisted for centuries with almost zero gene flow. Why did archaic and ceramic communities remain biologically separate while sharing the same small islands? Topography offers one clue. Many archaic camps cluster in rugged interior caves or karstic uplands, whereas ceramic villages favor fertile coastal plains. Add thick mangroves, treacherous reefs, and seasonal hurricanes, and even short overland journeys became ordeals. Cultural boundaries could have amplified that separation. Different languages, dietary rules, and ritual calendars may have discouraged intermarriage just as effectively as mountains or reefs. Critical swaths of the map remain unsampled. Hispaniola, the largest island and probable contact zone, has yielded almost no ancient genomes. Likewise, Florida's wetlands and the Yucatan's cenotes could test the proposed North American link, while additional Orinoco sites might clarify the ceramic launch point. Until those gaps close, the Caribbean's genetic jigsaw will keep a few pieces stubbornly missing. Imagine plotting every genome as a dot in multidimensional space. PCA flattens that cloud into two axes so clusters, shared ancestry, jump out at a glance. Think of F4 as a genetic lie detector. By asking whether population A shares more alleles with B or C, it spots hidden affinities and measures their strength. This program treats a target group like a smoothie. Given a panel of source populations, it estimates the percentage each ingredient contributes, perfect for modeling ceramic mixtures. Where QPAD-M asks, how much? QP-Wave asks, how many? It tests whether one, two, or more ancestral streams are needed to explain a data set, flagging overlooked migrations. Together, these tools turn degraded DNA fragments into a navigable map of prehistoric journeys. The ancient DNA breakthrough reframes Caribbean prehistory as a tale of at least 3 daring seaborne pulses, not one slow trickle. That insight ripples far beyond the islands. It spotlights the America's northern littoral as a potential launchpad for Holocene voyages and underscores Amazonia's role as a powerhouse of culture-bearing migrations. Interdisciplinary payoffs are already emerging. Linguists can now test whether Arawakan dialect splits track the QPADM stepping stone route, while isotope chemists can pair diet signatures with genome clusters to see who farmed cassava first. For today's Caribbean communities, genetic evidence offers a new, sometimes unsettling, mirror on identity, prompting museums and descendant groups to rethink how they tell their own origin stories. Technically, the study is a proof of concept. If degraded tropical bones can yield 1.2 million SNP genomes, then rainforest Africa, Southeast Asia, and Melanesia are next in line. The coming decade will likely swap a handful of pioneering datasets for continent-scale atlases, letting us trace humanity's blue water odysseys with unprecedented precision. Ancient genomes have turned Caribbean prehistory from educated guesswork into a data-rich narrative. The islands were first reached by archaic mariners, some with unexpected North American ties, then reshaped by Arawakan farmers sweeping up from the Orinoco. Against all odds, the two populations lived side by side for centuries with scarcely a trace of intermarriage, leaving genetic fault lines still detectable today. Beyond solving a regional puzzle, the study showcases how even the frailest DNA can redraw migration maps and invites us to keep probing the silences in humanity's deep, blue water past. Thanks for exploring the roots of Caribbean prehistory with me. If you enjoyed sailing through ancient DNA, give the video a like and share it with anyone who loves archaeology or maritime history. Curious for more? Check my other videos for deep dives into other genetic mysteries. Subscribe and ring the bell so you won't miss the next expedition. Until then, stay curious and keep charting the human story.